Welcome back to Applied Materials and Corrosion. Today we're going to talk about, or I'm going to talk about, a phenomenon known as overpotential. It's where a reaction at an electrode, an electrochemical reaction, would be expected to happen, but it doesn't because the surface is not right. So if we take a perfect reaction like this one, of copper to copper 2 plus in solution, it behaves very much like a perfect reaction. The copper and copper 2 plus are in equilibrium. They can switch out the whole time, and that means that if we increase the voltage in one direction, the current increases, and if we increase it a little bit in the other direction, the current decreases, and it goes through some kind of 0-0, not necessarily at the zero of voltage, but at the zero of voltage for copper 2 plus in those conditions. That is fairly understandable. But what if we make it difficult for the element or the ion to be discharged? So if we take a different case with a carbon electrode and two electrons have to hop off it onto protons in solution somehow, making hydrogen, then we have a relatively simple process. It's completely reversible if the electrode is platinum. If the electrode is carbon, it's not so easy to do. There are two problems. One problem is the electrons have to get off the carbon onto the hydrogen. Okay, there are more than two problems. The hydrogens are now effectively radicals, and they have to sit somewhere and find each other. They then have to connect back onto each other, and then they have to make a bubble of hydrogen, or it's dissolved hydrogen. Once the hydrogen is being formed, depending on what the state is, it can then leave. The main problem here is that the electron transfer and the bonding, the half bonding, is not facilitated on carbon. If we take an electrode where this reaction goes well, which would be platinum, the hydrogen ions can go one at a time. So we can have one electron jumps onto a hydrogen ion. It makes a platinum-hydrogen bond. And the platinum-hydrogen bond is almost exactly half the strength of a hydrogen bond. So if two of those are close to each other, there is no difference in energy, or very little difference in energy, to it being two on the surface next to each other and being hydrogen as a gas. So this would be the whole process. We've got our platinum here. An electron jumps onto a hydrogen ion. It forms a hydrogen-platinum bond. My arrows have got ugly. Forms a hydrogen-platinum bond. If there are two of those next to each other, they can collapse. So this bond can then bond to the other platinum, and this bond can bond to the other hydrogen. Or we can have a radical reaction where one electron from each goes in, one electron from each goes in. We don't need to know which that is. Then it jumps out and we have our hydrogen forming. That is very low in energy, so we don't have an activation energy. But for carbon, it's not the case. We can't attach a hydrogen to carbon, not to graphite anyway, and that's the only type of carbon that's reasonably conductive. We can't just attach an extra hydrogen to it because that would make it non-conductive. It would change its nature completely. Now I've redrawn that to be a carbon electrode. Our electron is jumping off the carbon onto the hydrogen. It should be a one-armed arrow for one electron. Then we either form a bond to the carbon, but as I said earlier, that could be a problem because once we've bonded hydrogen to our carbon, first of all, it's not graphite anymore, so it's not going to conduct. And then it's bonded on, it's going to be difficult for it to come back off again because we know that the bonding energy between carbon and hydrogen is very high. It's nearly as high as the bond between hydrogen and hydrogen, and we would have to break two carbon-hydrogen bonds and make a double bond to make our hydrogen back. So we might be stuck at this state if we go there, or we could make a radical in solution, but a radical in solution is also going to be very difficult to make. And so somewhere along here, either at the breaking of this bond or at the formation of this radical, we're going to have a very high activation energy. The activation energy means that we get a different current profile. So as before, the hydrogen to H plus is a reversible reaction. It can go in both directions, but there's an overpotential. There is an activation energy in between it, so we need to beat that with our voltage, either in the forward direction or maybe also in the reverse direction. It may be that there's no activation energy in the reverse direction, in which case we would imagine from thermodynamics for it to be here. But because there's an activation energy, it pushes the voltage up way higher. As we can see, it might very well depend on what the material the electrode is, or at least the surface of the electrode, and what the reagent in solution is. So it may vary depending on whether we're using one type of metal or another one, or a conductive polymer or carbon. So this brings us to a demonstration that I did last year. I'll link to the video with tin and platinum. Here we see tin. Here's the pour-by diagram for tin, just to remind us what that looks like. We've got tin 0 at the bottom here, so it's more reducing than even the hydrogen in water, so it can make hydrogen from water and it will dissolve. In most of the region, however, it makes tin hydroxide, which is solid. So between here and over here, it makes tin hydroxide, and that is completely stable. So tin, that's why tin was used for protecting food in the past. If we make it really basic, it dissolves, and if we make it really acidic, it dissolves. But you notice here pH 2, so obviously if we have some acid in there, we can exceed this region and we can get into here, which is tin 2 plus dissolving directly into the solution. So if we put it into a strong acid, 1 molar concentration will be at 0.1, so we'll be out here. So that's relatively easy to do in a chemistry lab. We can just drop it in some acid. If we do that, what we find is that nothing happens. So although our pour-by diagram predicts that the tin should be oxidized, form tin 2 plus, and the water should be reduced and form hydrogen, so bubbles of hydrogen should form, nothing happens at all. If we put a platinum electrode in, the platinum is completely stable. It's stable up here, and so it's actually stable above the oxygen line. Platinum doesn't oxidize even in concentrated oxygen, so then nothing happens. It's platinum 0 all the time, so we would expect nothing to happen, and it really doesn't. What becomes interesting is if we take our H plus solution, our acid solution, and we connect these two electrodes together. If we do that, the tin is now not limited by the overpotential of hydrogen forming on it, so the tin is trying to give away electrons, but it can't because of the activation energy here to form a tin-hydrogen bond. Instead, it can send the electrons around here and drop them onto the hydrogen from the platinum. This works and this does not. Whoops, I've drawn a backwards tick, never mind. This connection means that more current can flow than would otherwise do so. So now we've connected the other topic of corrosion to pour-by diagrams and electrochemistry, because the moment that we connect these two metals together, we've done a really bad engineering thing. We've caused our system to become unstable. As soon as we get into this acid region, the tin can now dissolve. The tin dissolves directly into the solution. You can't see it doing that because it's not that much, but the platinum is making hydrogen and it starts to bubble. If we put an ammeter in the middle, we can measure current flowing because the electrons are going to the platinum and jumping onto our hydrogen ions. This phenomenon is actually quite common and it's really useful. It's also a problem in some conditions. So it's really useful because obviously the tin, even though it is thermodynamically unstable and should form tin 2 plus ions, it's blocked kinetically by the activation energy of making hydrogen, so you can still make a tin can out of it and put sour fruit in there and it still doesn't poison you. There is a problem, obviously, as people found. If you use other metals, then you can cause it to corrode much, much faster and then poison everybody. The other thing that we can do if we're trying to measure things with electrodes is we can extend the region that we can measure in by using a metal that is not very good at breaking water in the way that we expect. So if we're going to a negative potential, a platinum electrode is terrible. We can't go very far and it starts to break the water and make hydrogen. But if we use a carbon electrode or a tin electrode, it is much more difficult to reduce the hydrogen and they are stable. So we can get to a lower voltage, more negative voltage, and nothing happens. On the oxygen end, there is another electrode for the oxygen end. So on the oxygen end, if we try to... So if we're going to a positive potential, tin would be a good example of an electrode for that, although carbon is actually better. If we go to a positive potential, we're corroding our electrode, but platinum isn't a good electrode. It's very stable, it doesn't dissolve, it doesn't get worse, but the platinum catalyzes the reaction of hydrogen, and so it limits our possible window before we get lots of current and we can't measure anything. So it's better, very often it's better to use carbon electrodes or mercury electrodes originally, so that hydrogen isn't formed, and then we can measure at a more positive potential. Going in the negative direction, platinum is actually an excellent electrode, and mercury, for example, is a terrible electrode. It allows oxygen to form far more easily. Carbon is also not a great electrode for going in the negative direction because oxygen reacts with the surface of the carbon, forming carbon-oxygen compounds, and so the electrode is eroded really quickly, and it has a relatively low overpotential. For one of the experiments that we do, we deliberately use a carbon electrode and a platinum electrode the other way around to minimize the voltage that's required to electrolyze water. It does mean we get carbon dioxide typically and hydrogen, but the voltage required is much lower than if we used a platinum electrode and a carbon electrode the other way around, because the overpotential is way higher. So then we come to the question of what an underpotential is. It's a word that's made up just to show that it has a similar effect to the opposite of an overpotential, so we see less voltage, less required voltage than we would expect for a process, and that would be in the case where we get some energy out which we weren't expecting. So we take a lead electrode and we're trying to coat it with lead from solution. It's got relatively low activation energy. The lead ions can join on to the surface of the lead, and this new surface of lead looks exactly like the old surface of lead, so we're not making anything different. So the total interfacial energy is staying the same. If we make it rough, then it's costing us some surface energy, but if we're increasing it gradually as a flat layer, we're not doing so. What if we take some copper and put it into lead, however? Then we get a lead layer on our copper. Let's make the lead blue. So let's make the lead blue. And we put some lead ions on the surface and they start to make a lead layer. They might not be a full layer. Let's have one every other, in fact, to denote that. So they might form a half a layer of lead in the holes between the copper atoms, or some other lower amount. Those lead atoms are filling up where the copper was particularly unhappy and had extra dangling bonds, and so they reduce the energy of the system, and therefore these atoms of lead are easier to deposit on copper than they would be onto lead. If we carry on, we'll end up with a lead layer and it will behave just like this. What does that look like in a electrochemical manner? So if we have a piece of lead and we put it into an electrochemical system with some lead ions, then we would expect some type of curve like this. It's not exactly linear, but I've modified the axes so that it does appear to be linear. If we go to a positive voltage, it goes up, so we're dissolving the lead. If we go to a negative voltage, we deposit lead, and the lead increases with voltage. If we take a piece of copper, we can't make lead dissolve into solution up here because there isn't any lead. So obviously it can't follow this curve. As we come along, before we get to the potential when we would normally start to grow lead, we grow this small layer. And depending on the sweep rate, we get a little peak, and the peak is limited. So if we do it very, very slowly, we get not very much current, but for a really long time. If we sweep very fast, we get a very sharp peak. If we also measure time, we can measure the amount of current that flows, the amount of charge that flows inside this peak, and work out the area of our copper electrode. When we've finished covering it with a layer of lead, then it behaves just like lead, so nothing happens again until we get to here, because it's still just copper with a layer of lead on. Even if we go back up, it won't come off. Then it will go down this line. What will happen if we go back the other way? Well, if we go back the other way, obviously our lead will come off. The lead that we put on there will come off. But if we stop and let the lead come off so that we've got none apart from this layer here, we will then also get a peak in the positive direction. Let's put it slightly further up because it's more logical that way. So we get a peak in the positive direction, and its volume should be about the same. Depending on the sweep rate, you can make it look different, but really the amount of charge passed in this peak is the same as the amount of charge passed in this peak, because it's just a number of ions required to make this partial layer. If we know how dense it is, obviously we can calculate the area of the copper, but it's a useful phenomenon. Okay, that was a short one for this time. There are plenty of other topics, but I don't want to mix them up in the same video. We'll come back to something else.